Hello everyone. In this tutorial, we are simulating OFDM transmitter and receiver in GNUradio, and we start with our file source, that is inputting a TXT file that will be transmitted from the transmitter and received at the receiver, and the contents will be displayed on the terminal. Um, Using UDP port. So let's start with the file source. So the file source takes in this variable, the the location of the file, and it converts the file into bytes. And since we are using everything we are doing everything in software. We do not have any hardware connected to our laptops. The hardware I'm talking about is USRPs, software defined radios. So we have to have throttle block in our system, and this is what we are having here. The next block is stream to target stream, converts the stream into a packet, and the packet length is right now 92. It is set to 92. These packets will be appended with CRC, and CRC adds 4 bytes, so now the total packet length is 96 at the output of CRC here. Moving on to next block, repack bits. So it unpacks the bytes, and each byte contains 8 bits. So we are unpacking all these, all the content of the byte, um, by having this configuration. So the number of bits in the input here is 8, and the number of output is 1. So so we are actually increasing the size of the packet after repack. And why we are doing this? Because your forward error correcting encoder works on single bit in a byte. So right now, the packet size is configured with 96. This is the byte, and the bits that it works on is 96 multiplied by 8, and these are the frame bits that it works with. It is half code rate convolution encoder with constant length of 7. Polynomial is defined here. So these are generally only this parameter that is configured in this tutorial. Rest everything is by default. Moving on, after forward error correcting encoder, I'm using block interleaver. Block interleaver defines interleaver indices. Based on these interleaver indices, it shuffles the input bits and interleave them so that they can work around with burst errors in the channel. Moving on, since we are using 16 QAM in this tutorial, so we will be repacking over um, bits into 4 bits per byte, and these 4 bits per byte is then digitally modulated using 16 QAM and converted into um, uh, complex numbers. This payload mod is defined here in this variable. As you can see, I'm using 16 QAM. Moving on, we have very traditional OFDM processes here. OFDM carrier allocator takes in different parameters: sync block 1, sync word 1, sync word 2, pilot symbols, pilot carriers, occupied carriers, and then IFFT is happening here. after IFFT cyclic prefix. And for this tutorial, I'm not using an actual channel model, but we can definitely use this channel model here or this one. Both of them can be applicable in this in next tutorial, which will be a shorter version of this tutorial. I will be using actual channel models. So right now we are using frequency shift that will introduce carrier frequency offset to our OFDM symbols, and some timing offset in order to introduce some timing offset in our symbols. And these two can be can affect our detection process in the receiver if they are not compensated at the receiver. So moving on to the receiver side, um, that is I'm using virtual sync here, virtual source here. So the first block is synchronization block that actually takes into account FFT length, cyclic prefix, and the threshold that we will be noticing. So this synchronization blocks helps against measuring or calculating the timing offset that we are introducing here. So once this synchronization blocks measures um, the timing offset, it will send a trigger message and the frequency offset. And this trigger message is converted is going through an interpolating FIR filter, and it has the size equal to the frame size. So this trigger message gets multiplied with our receive symbol, receive signal, and act as a gate to transmit to not to transmit but to pass our signal through to detection process. So if there is no detection, there is no signal going through the detection chains. Um, so once we have our signal here, which it will be um, frequency offset compensated using this flow chain. So frequency offset is also computed in this block. Then we do the frequency modulation, multiplies it with our receive symbol, receive signal, and we have our clean signal. Then we will take out the cyclic prefix and convert the stream into vectors, take the FFT, we will do the channel estimation. Now, one thing I would like to say, we have synchronization words that we will be using in order to estimate the channel and the number of data symbols. And then we will have frame equalizer, and uh, that will perform the equalization because we are not having any channel here. So this equalization is redundant here. So it is not doing any it is not making any impact in our chain. OFDM serializer converts the vectors into a samples and gives out the samples. So these samples are being received by virtual sync, virtual source here, and goes into the constellation decoder. As I mentioned, we are using 16 QAM, so it is a 16 QAM decoder doing the exact opposite of what we are doing in the transmitter side. So we will be repeating the same blocks but in an opposite direction. So because our constellation decoder gives out 4 bits per byte, But since, as I mentioned, that FEC encoder and FEC decoder, they works on 1 bit per byte, so we have to convert everything to 1 bit per byte. Because we are using FEC decoder, um, it only takes in soft symbols at the input in the float, but we do not have any noise in our system, and in order to produce soft symbols from the documentation, we can see that by simply converting zeros and ones into -1 and 1, we can make our decoder work with hard decision. Interleaver is happening before the decoder, using the same principle, the same indices we used, and similar to what we are doing in the transmitter, we are doing the opposite, uh, because it works on 1 bit, converting it back to 8 bits, and uh, then we have stream to target, stream to 96, and CRC and UDP. Now let's try and see how this works. So let's see what our file contains that we are going to transmit across this OFDM system. So our file contains this message, and then we can run our flow graph in order to see our transmission or receiving at the receiver. We should be looking at this port. Okay, so let's see what this port says. Yes, we are receiving our messages and everything is working fine. So we can stop it. Thank you. Another demonstration would be to send a video across this OFDM symbol. So the only change I made is having a UDP source that will be configured with VLC, and the VLC will be streaming a video across this OFDM flow graph, and we will be receiving a VLC video on this port. So the port on the transmitter side is 2222, and the port on the receiver side is 6666. So let's start the video transmission. So on the transmitter side, we are initiating a VLC process that will stream the video across. So let's stream it. So the video is already going on. We have our um, uh, flow graph running in order to see the video transmission on the receiver side. Let's start another VLC with this parameter. There you go. So we have our VLC video being received at the receiver side using this flow graph. There are some lags, which may be because of the wrong packet size. So one thing that we can definitely do is change the packet size here, because it's an MPEG TS frame, so the packet size should be 188. So now we have our packet size change everywhere 188. Now let's try the video again. Let's first start our flow graph. Start. There you go. It is more smoother now as compared to the last time, but yeah, still lag is there because of the slow computational processes, uh, slow computer, and the computation is happening on a single computer, so that is why we are seeing some lags. So thank you very much. I hope you enjoyed this tutorial. Until next time, bye.